Hello again, and welcome to another installment of the 8-bit breadboard computer project series. Long ago, when the four nations lived in harmony, I promised a program that would generate prime numbers on the 8-bit breadboard computer. This program would demonstrate the bit shift functions of my computer's ALU and the expanded memory. Today I've written that program, and I'm going to go through it with you in this video. So first, a high-level overview of the program. This is a simple primality tester where you could input a number and the program would determine if it's prime, and that is run iteratively for numbers from 5 to 127. The program outputs 2 and 3 in a hard-coded manner because it was easier to just output them than try and implement that into the test, where for every number that's not 2 and 3, we would be wasting time on a check to see if the number was 2 or 3. For each number, it checks all the possible divisors up to the number divided by 2. We could, of course, check all the way up to the number, and these would also be properties of primes that none of them except the number itself would divide it, but checking those is unnecessary. In fact, checking anything above the square root of the number is unnecessary. But on this machine, we don't have access to multiplication, division, or modulo as a hardware function. If you were on a real computer and you didn't have access to a math library, to get the square root function to determine how high you need to check divisors, you would simply square the divisor every time you increment it by 1, and then you would compare that against the actual number. If you did have access to the math library, which is going to have some fancy logarithmic approximation that's probably constant time for whatever sized integer to compute the square root, you would obviously use the math library's square root function. Since we don't have that, we just do a bit shift 1 to the right, we divide by 2, and that's certainly better than checking all the way up to the number itself. It at least saves us half the time. While it's still an order n algorithm this way, it's certainly better. Now, so that demonstrates the bit shifts. I also said that we don't have access to modulo, so we're going to have to write that. We're going to have to do it iteratively with the addition and subtraction functions that are available with this ALU. So as part of this program, there's a modulo subroutine, which takes an argument of the number we're testing, the number that we're dividing by, and then returns its result in a third global variable in the program space. And then we can use that result to determine if it's prime. Obviously, if we have a divisor, the modulo, the remainder, will be 0. So that will tell us that it is not prime. And if we have no divisors all the way up to the number that we are testing divided by 2, then we do not have a prime. So it would be rather tedious to step through all of this program for high-value numbers, but I will go through some of the instructions for the lower values, and then I'll give you some tips and tricks about what to look for to see how this program is running, even when it's going full speed. There are still things with the blinky lights that are not too fast to observe other than just the output to get an idea as to what's going on. So first things first, we're going to stop the clock and we'll reset the program. So now, stepping through the beginning of it, the first thing I said that it does, it outputs hard-coded 2 and a hard-coded 3. So a quick review of what we're looking at on the board. We have the A register, which is the accumulator, the B register, the argument register for the ALU, the output of the ALU, the bus, the red here, the green here is the program counter. This is where we are executing in memory. This is a jump indicator LED. We have the memory address register in yellow here, and we have the contents of that location in memory here in red. And then we have the instruction register down here. So instructions end up here and they tell the ROMs what to do. And then down here is some control word stuff that you're not going to be able to make much sense of with how quickly that's going to move. And I have the label bar removed at the moment. So, stepping through the program, first thing that's going to happen is this first instruction is going to get loaded in the instruction register. So it goes in the fetch cycle, it goes out onto the bus, and then it gets put into the instruction register before this instruction itself begins to execute. Now, after that, this instruction is doing a load A immediate 2. So the upper nibble, which is the lower nibble, the little nibble, is these 4 yellow LEDs here, is on the bus, which is a 2, and that's going to get put into the A register. Then we're going to advance to the next instruction. The next instruction is an output A instruction. So that's going to get in the instruction register. A is going to go on the bus. It's going to go into the display register, and then displayed on the display in decimal, because that's how I have the output format set right now. The next 2 instructions are going to do a very similar thing, but they're going to do it for the number 3. So we see 3 ends up on the display. The instruction after that, at 4 in memory, is going to end up putting 5 into the A register. So 5 goes onto the bus, goes in the A register in the same way. That's a 1-5, load A immediate 5. And then from here, the next instruction is different. This is a 0-3, which is a store A command. So this is going to go into the instruction register, and then this is going to tell it to fetch the next value in memory and put it in the memory address register, which is saying what's in this location of memory here, and we're going to be loading the 5 into it. It did that already, so we see that in F1, which is our number under test variable, 5 is loaded. Now we're ready to start doing the testing. So the next thing that happens is we go back to where we were executing, program counter's at 7, and we do the division by 2. This is the bit shift to the right. So we're going to load that in the instruction register. Then we see the A register being shifted 1 to the right. 5 divided by 2, truncate it, is 2. Now that result's going on the bus, it's going to end up in the A register. And then the next instruction is going to store that value, so 0-3, and it's going to store it in a variable we have reserved for the test number divided by 2. That's F2. So that's going to go there in the memory address register. Then the bus goes out. It goes out to the bus from the A register and goes into that memory location. After that, we're going to load A immediate 2, 1, 2. Same as the first instruction in the program. So 2 got loaded in there, but there was already... there we go. And then we're going to store that result, the 2, into a variable reserved for the divisor count, which will be at location F3. So we have a 2 there. Now that's the number that's going to count up and divide our test number. So that's going to go 2, 3, 4, 5, and divide our test number all the way up till the test number divided by 2. So the next thing that's going to happen is we're going to do a jump instruction, which is a 6-0, and we're going to go to memory location 60, which will end up in the program counter. We saw that value end up in the program counter, and now we're executing at 60. This is the modulo subroutine. All this is going to do is subtract from the current number the divisor. From the test number, it's going to subtract the divisor until the result is less than 0. After the result is less than 0, it's going to add it back once, and what's left in the accumulator is going to be our result. So if we watch that happen, the first thing that happens is we load A, F1, the number under test, so 5 gets into A, and then we subtract F3, and that will be the number 2. So we're going to take modulo 2 by doing repeated subtraction. 5 minus 2 is 3, and then there's a jump instruction that says jump greater than 0. So this is greater than 0 because the sign bit, the far left bit, is not set. So this is going to go back to that point where it does the subtraction, that instruction, that 3-0 right there. That'll end up in the instruction register. And then we'll do another subtraction of the value we're dividing by, which is again a 2. It just pulled that from memory, put that in there. And then we do the subtraction. We have a 1. We'll do this one more time. And then this is a negative number because the far left sign bit is set. Then our jump greater than 0 won't happen, and we walk right through it. And this 2-0 instruction is addition. We're going to add F3, so we're going to add that 2 back. It's going to load that 2, do the addition. Then we have a 1 in the A register. Now we're done. And it's going to store that value into F0, which is our modulo result, global variable. Stored the 1 there. Then we jump back to 0F, which is where we made the modulo call from. After we jump back, it's going to load into the A register the modulo result. It's that 0-1 there. And then it's going to check it. It says jump equal to 0. And if it is 0, we know we have a divisor, so it's not prime. And we would just increment the test number. But that's not going to happen because this isn't 0. So instead, we're going to load A, the test number divided by 2 at F2, which is a 2. And then we're going to subtract the test F3, which is the divisor count, and that's a 2. That'll get in the B register. And we do subtraction. That result is 0. That result goes into A. Now, our next instruction at index 1-7 is a jump 0 command. So if we're equal to 0 here, we know that we've reached the end of the numbers we've had to test, and we've never taken the other jump option, which means that this number must be prime. So then we're going to jump to the subroutine at 2-9, which outputs our value as a prime to the display. So 1 is a load A. We're going to load A F1, which is the 5 we were testing the whole time. Then we're going to output that to display, and the 5 ends up there. After this, we jump unconditionally to 2,0, and that is going to load A, the test number. This is going to increment the test number, this subroutine that we've jumped to here. So this is F1, got loaded, or will get loaded shortly. And then we do a 2, 2, which is a increment by 2 immediately. So 5 plus 2 is 7. And then we do a jump less than 0. So if this were a negative number, we're done. If it's not, we're going to ignore this. We're not going to go to address 0 like it's showing right here. Instead, we're going to store A in F1, which is the new number under test, is now 7. And then we're going to jump unconditionally back to 0, 7, which is the bit shift instruction at the start of the test. So we end up back at 0, 7, and we can see the instruction is 4, 8, which is the bit shift. And we're going to do 7 shifted to the right, 1, which is a 3, that ends up there, and we repeat this process for all the primes. So if we let that run, it'll start displaying primes on the display. Now, even while this is running really fast and you can't really see much of what's going on, certainly you could see the program counter advancing. You can see when we're in the modulo subroutine by when those 2 LEDs are on, indicating a 6 in the upper nibble there. You can't see the T-state counter, you can't really tell what's going on in the memory. But if you look at the B register, this will tell the story of what the modulo subroutine is doing. And this can give you an idea of where you are in between the current prime displayed and the next prime that will be displayed. This number here, the highest number that you see being on the B register for a little bit, is the number we're dividing by. And you can watch that increment up. So here we're dividing by 2, 3. Found a divisor. 2, 3, 4, 5, 6, 7, 8. And you can watch this and get an idea for where it is. You can also pause the program, go into memory read mode, and look at F1, which we know is our number under test, and we can see that this is a 1, 9 in hex. So 19 in hex is 16 plus 9 is 25. So we're testing 25 right now. The last prime we displayed is 23, so that, of course, makes sense. Making sure to put it back in run mode, then start the clock again and continue. So that's about all there is to the execution of the program. Now, there were a couple of quirks that people asked me about when they were viewing this in person. One of those is related to the very last number in the sequence. 127 is a prime number. I believe it's the next prime after 113. Now, when the numbers start getting very large, it takes a long time to test them, on the order of 2 minutes or more sometimes. The whole program to run from 2 to 127 and to reset takes about 22 minutes at this clock speed that I have set here. And people have asked me, why didn't it display 127? Well, they weren't staring at it for 22 minutes, and in the video that I'll show you in just a moment, you'll see that it does in fact display 127. It's just that at the end of the program, it outputs to the display, then it jumps. It's 2 instructions to jump back to the increment test number subroutine, which is 2 more instructions to load the test number, 1 more instruction to add 2 to it, and then 2 instructions to do a jump less than 0. So that's 5 instructions between displaying 127 and resetting the program, displaying 0, because the 0 is the display register, 0, 2, 3, and then testing 5 and continuing with the test. So not very much time to see that, and it'll be comparable to the amount of time that 2 and 3 were on the display just then, which is not very long. Easy to miss if it takes 2 or 3 minutes from displaying 113 to roll over, and it rolls over within 5 instructions. So I'll show that video to you now, just so you can see that the sequence is in fact correct. One more question I get about this program is why I choose to write it as an iterative primality test, as opposed to using the standard space-time trade-off approach of the sieve of Eratosthenes. This is a method where you only divide the current number under test by all the previous primes that you've computed. Of course, you have to start from the beginning of prime numbers or have a list of primes less than the prime that you are testing, but this approach causes you not to have to do so many divisions. When you compare it to even the more efficient order root n, as opposed to the order n approach I have right here, wherein you have access to a constant times square root, it should still outperform it, provided you have the space. Now, I certainly have the space. There's only 127 numbers that I considered in this test, and if you look at all the primes less than 127, there's on the order of 50, maybe even less than that. I've used about 50 bytes of program space to make this program, and I have 256 bytes available. So I probably could fit 50 more bytes worth of primes to save me some divisions. Now, I could have done that, but this computer, like most modern computers, is what we call Princeton architecture, which means that the program memory space is in the same physical memory as the runtime memory space. In this case, these 256 bytes on those SRAM chips right there. The SRAM chips are kind of difficult to program. The only way to do it is through these two interfaces right here. This one, where you enter the value, and this one where you enter the memory address. And then you have to write in every single byte by hand. Now, if you're using 4 global variables, and those are the only locations that you're sending write commands to, it's pretty unlikely that you're going to overwrite your program. And I've spaced them pretty far away from my program, all the way at the end of memory, in addresses that start with OXF0, and then go down the list from there. But if I made a list structure, it's quite possible that I could end up writing the list past the edge of memory, have some overflow, and then start writing numbers on top of my program space by making only a simple mistake, forgetting to terminate a loop that's been constructed out of jump statements. That would be really annoying to debug. So for a first test of this, I just wanted to do a primality test, and that demonstrates the need for more memory than 16 bytes, and it demonstrates a use for fast division by 2 using my bit shifts. Anyhow, I hope you've enjoyed this video. Please remember to like and subscribe if you want to see more content like this, and do science.